between the direction and the gravitational pull constantly change. All right. So if you want to do this from first principle, you would need to know the exact mathematical description of the curve, and then you would need to do integration and so on and so on. However, what saves you here is the fact that gravity is indeed a um, a conservative force. So it cares only about where you start and where you end up. That's all what you care about. So that's why you're going to use energy method to solve this problem, to do this problem. All right. So let's go back to this here. Yes, Meta, do you want to add something?
No, I'm good.
Okay. So find the speed of the coaster and find the speed of the coaster at the end of the ride. All right. All right. So the first thing you want to do when you do a problem with energy is you have to give your system. All right. And here the system will be as follows. Of course, it will be like the coaster, the car, right? However, if you want to make use of gravitational potential energy, so it's something I'm going to stress here. I'm going to stress it even like more like next year. If you want to make use of gravitational potential energy, remember I told you potential energy always comes as a result of interaction with other bodies. So if you want to use gravitational potential energy, you have to use also the Earth. All right, so you have to use the Earth. So if you don't put the Earth as part of the system, you cannot use gravitational potential energy. You'll have to go back to the you'll have to go back to the work energy theorem. All right, so it's a little bit, yeah. You'll have to go back to the work energy theorem and the work done by gravity. And whenever you do like the work done by gravity here, you'll have to go back to the original definition of work, which is F times delta D times cos theta. All right. So if you want to use the potential energy, then you absolutely have to include the Earth. So let's put the Earth here. So put the Earth. Okay, and then we'll put the rail here. Okay, so the coaster is on rails. So this is your system here. Now let's have so this is the cart here. I have a little FBD here. Now the rails does exert a force onto the cart here. All right, it does exert a force onto the cart. What type of force does the rail exert here? Yeah,
A normal force?
Yeah, a normal force, right? There is a force exerted by the rails on the cart so as to keep the cart on the rails. You don't want the cart to go off the rail. So there's a force exerted by the rails that will be like 90 degrees perpendicular to the rails. Since we're dealing with no friction, so we're going to assume here there's no friction. So the only contact force from the rails is the normal force, right? Now, normal force might be like towards or outwards. It doesn't really matter here. I'll put it in here, right? So would be in. All right. And that's it. So Now, do we care about the work done by the rails? Yeah, Madav.
No, because it's perpendicular.
That's correct. All right. So the work done by the rails is 0 because the rails exert what we call a constraining force. All right. And what a constraining force is a force. All right. So right. Let me put it here. So a force, okay, so a force that constrains an object to move along a particular path. All right. So constraining force is the normal force in this case here, and it constrains the coaster to move along a path, along the rails. And work done by a constraining force is always 0. There's never this. In most cases, it's not exactly true, but in most cases, okay. So constraining forces all right, never, I'll put this here in bracket here, never do work. Okay. So whether so the constraining force for the most part will be the normal force. And the normal force being like either 90 degrees perpendicular direction of motion or the force provided by normal force does not move. All right. So in any case, the work done by normal force will always be 0. Okay. For most cases, not all the time, but for most cases, it's going to be 0. Okay. So whether the normal force is conservative or non-conservative is not really important because the work done by constraining force will be 0. Okay.
Sir,
Yeah.
could you also just say that like the rails don't move, so the work done is on of the rails is
Yeah,
zero?
you can say that too. Sure.
Okay.
Yeah. Okay. All right. So now let's go with this. So now we've put the systems. And now what we're going to do here, since you have only conservative forces, since only conservative forces are involved, all right, so what do we have here? We have the mechanical energy will be conserved, all right? If you want to put it in this fashion, you can put it in this fashion. If you want to put it in delta K is equal to minus delta U, that's fine, okay? So mechanical energy, actually the mechanical energy all throughout will be conserved. So let's put this here. So mechanical energy is kinetic energy plus potential energy equal to the final kinetic energy plus the final potential energy. All right. So once again, I'm going to sort of explain this a little bit later, next year. So if you want to sort of use the gravitational potential energy, you have to put the Earth as part of the system. Why is the Earth not part of it? Why do we not care about the kinetic energy of the Earth? Well, you might sort of guess it's because like while this thing like goes down, the Earth will hardly move. All right. So that's another case here where like the Earth is so much more massive than anything else that there's hardly any change in kinetic energy. So that's why we don't put like the kinetic energy of the Earth. So I'll come back to this next year. Okay. But the key point here, if you want to use a potential energy, you have to put as part of the system all what gives rise to this gravitational potential energy. So it's not only the coaster that has gravitational potential energy, but it's the coaster and the Earth. Okay. If you don't put the Earth and you put only the coaster, then you cannot use potential energy. You'll have to fall back on the work energy theorem. Okay, so there are a couple of things here we can do. We can cancel here, or that goes away. Of course, that the kinetic energy here is 0 because the speed initially is 0. And now we put this. So it's going to be mghi equal to mvf squared over 2 plus mghf. Now, notice here that I did not give you the mass of the coaster. I could have given you the mass of the coaster, but in this case here, you can see here that it does not matter because the mass will cancel on both sides. All right, so here, so you have mass, it goes away. So that's very interesting here. So what does that mean here? It means that no matter what the mass of a coaster is, no matter what it is, if we have the same conditions, no frictions, and it starts at 50 meters from the ground, ends up at 5 meters from the ground, all those coasters, no matter like how many people on the coaster, they will all have the same speed at the end of the ride, no matter what the mass is. But this is only true, of course, if there's no friction. Okay, if there's friction, that's something else. It may or may not. Yeah, Max.
Wait, so is this also the reason why when we watched like the vacuum video, the feather like fell at the same speed as the brick or the rock
When
or whatever?
you watch the what? The vacuum video?
like the videos where they had the feather and the bowling ball in the vacuum.
Oh,
because it was only
well,
it was,
yeah, it's kind of related. Yeah, if you wish, yeah, if you wish. Okay, good. So now, yeah.
I think you put the arrow for the normal force in the wrong direction.
No, it doesn't matter. Okay, I could have put it here or here. It doesn't really matter. Okay, all right.
Doesn't it point away from
it does not matter. Okay, so if you want to put it like away, like put it away. All right, it doesn't really matter here. Okay, because the work done by the normal force will be 0. Okay. Okay, Forrest. Like
okay.
Next year, we'll talk a little bit more about this. Actually, the normal force can be one way or the other, depending on the speed and so on. Okay. All right. So let's go back. So what we want is we want to isolate for VF. So I'm going to sort of do a couple of things here. I'm going to sort of move this term on this side. All right. So I'll just do algebra here. So GHI minus GHF. I can of course factor out G. And then, by the way, here, like this equation here, you could have gotten hit very much quicker if you had used
Wait, how come there's
Sorry,
still
how
come there's still
yeah,
an M?
Jason.
How come there's still an M on
The
right
thank
side?
you. Thank you. Just testing you, Jason, to see if you're there. Thank you. You could have gotten this formula if you had started with this right away. All right. There would have been this. All right. So once again, you can use this if you want. You can use that, or you can use delta m is equal to 0. Okay, it doesn't really matter here. Okay. Okay, good. So VF here will just be equal to this. Yeah, that's it. It's square root. So let's do this here. So 2 times 10 meter per second square. This is a G here. It looks like a Q. G, there we go. So the initial height was 50 meter. So 50 meter minus 5 meter. So you can see here that using unit, I'm going to get like meter square per second square. When I take the square root, I'm going to get meter per second. And this will be like 45, so 4, so 900. Oh, look at that. Does it give you like 30 exactly?
Yeah.
Ah, yeah, I'm very good these days. I use numbers out of my head. That works out like pretty good. Very proud. All right. Very good. All right. So here what we did is that we used the fact, yes. So chat, who wants to chat with me? Yeah, okay, smurfing again. Yeah, I guess. Smurfing. So now I want you to appreciate the fact that you could do this problem a lot easier by using conservation of mechanical energy. Okay, so this is very important for you to see that. All right. If you do not use gravitational potential energy, then you can use, of course, it's going to go back and forth, like it's a little bit laggy here. Okay, there we go. If you don't use like energy, if you don't use potential energy, you can always do the problem using the work energy theorem all the time. But once again, if you use the work energy theorem, you have to go back to the original definition of work, which is F, which is the scalar product of the force times the displacement. And in this particular case, as we saw, the angle constantly change. So it's really, really hard for you, unless you know like the exact mathematical description of the curve and so on. If you know integration, you can do this. Why would you do that? Since you know that gravity is conservative. Okay. So questions? Okay. Now I'm going to ask you a question here. So what about if instead of having this curve here, if the curve, don't write this down here, but if the curve had been this instead, can anyone tell me what the speed would be? Would the speed be the same, different, lower, higher? I don't know why I don't see anyone. Eric, you, there we go.
It will be the same.
It will be the same, exactly, because it doesn't depend on the path. Very good. So what about, well, now I'm starting with 0 meters, so I could not I could not have the curve like going like this, right? I couldn't have the curve going like this because it's 0 meter per second here. If you try like to use conservation of energy on a path like this, okay, I'm going to tell you here that you could sort of get the same answer. But the problem that you're going to have at some point is the following. You're going to find at some point that the kinetic energy will be negative. And that's, you remember, kinetic energy can never be negative. So what I mean here is that this equation could still be true for this path here, right? But at some point, the kinetic energy will be negative. So even though mathematically it's okay, physically it's not okay, all right? So that's why in this particular case here, like this will not physically be possible, all right? So having 0 meter per second, the car by itself cannot sort of go against gravity, okay? Even though, like from the point of view of energy, point of view of the mathematical equation, this will still be true, okay? So just there we go. So don't write this, okay? Okay, questions? All right. Sometimes you will need the mass, okay? Sometimes you will need the mass because, especially if you deal with the spring, if you put like spring energy, spring potential energy here, well, you remember the formula for the spring potential energy is K delta X squared over 2. So you won't be able to cancel the mass on both sides because you're going to have a K somewhere, all right? So whenever you deal with a force beside gravity, you may need to carry the mass, okay? All right. So what I'm going to do here, like for the next 10 seconds, not 10 seconds, for the next 10 minutes or so is, so we look at case B, we look at case A, only conservative force present. Now what I'm going to do here is I'm going to start case B. So case B will be when there are non-conservative forces present, all right? So case B, non-conservative forces are present. Are also present. All right, so case B, case A was only conservative forces present. Here, we're gonna sort of put non-conservative forces as well. It's the same equation as before. So we have a certain mass. So let's look at our roller coaster. Same as before. That's for later. That's for tomorrow. Tomorrow we'll do an example with this for now. Okay, so it's going to be the same height. So final height will still be 5 meters from the ground. Still going to be initial height, still going to be 50 meters. Now what we're going to have is we're going to put like non-conservative force. So let's say here. So this is our coaster right here. So now what we're going to do is we're going to have, of course, gravity. We're going to have normal force. So just to appease Forrest, I'm going to put in this direction here. And the most famous non-conservative force is, of course, friction. So I'm going to put it right here. Friction from the rail. Okay, we're still ignoring friction from the air. Okay, so friction from the rail. So these two forces here is the force from the rails, right? This is you remember contact forces can be decomposed into two perpendicular direction. One that is a component that is perpendicular to the surface of contact. So the rails here will exert a force on the car to make sure that the car stays on the tracks. And then here, like the rails will also offer like friction, okay, in the opposite direction. Okay, so we're going to the general case here. So the net work done on an object of mass m will be the work done by all the forces. We're going to put all the work done by conservative forces together, and we're going to put all the work done by non-conservative force together here. Okay, so NC. And we're going to call this 3. Now, once again, remember like using the work energy theorem. Right, that was like equation 2, I believe, right? And comparing 2 and 3. 2 and 3, we get the following. So we're going to get this. All right. So the change in kinetic energy of an object will be equal to the net work done on this object. All right. And here we put like all the work done by conservative forces together, all the work done by non-conservative forces together. Case A, we make this equal 0 because there was no only conservative forces existed. So, but now we're going to put like some non-conservative forces. Now, the advantage of work done by conservative forces does not depend on the path linking the initial configuration system, final configuration system. What we care is only where it is, where it is, and where it ends up. So the work done by conservative forces can be replaced by a function that we call potential energy function. Now what I'm going to do here is I'm going to bring like this on this side. This, I can put it like this if you like. Right? And what is kinetic plus potential energy? Well, it's mechanical energy. So what you have here is this. What you have to conclude is then where there are non-conservative forces present, the mechanical energy will not be conserved. In general, this is going to be different from 0. All right. So in presence of non-conservative forces. Right, mechanical energy is not conserved. Does not stay constant. Does not stay constant. Okay. Or is not conserved. All right. So this equation here, you can use it for the general case. When you're dealing with conservative force, well, this term is 0. And mechanical energy, so there's no change in mechanical energy, right? So you can only remember this formula and you'll be good, okay? All right. So I'll continue on this like tomorrow. Today you'll have to do like some homework regarding conservation of mechanical energy. All the problems I'm going to give you today, they're all, you have only conservative forces, right? So mechanical energy will be conserved, okay? And then later on, I'll give you like problems dealing with non-conservative forces, okay? Okay, questions? No? So remember I told you like earlier here, like if you want to move to Tuesday and Thursday or something like that twice a day, the sole reason why I wanted to sort of offer this is because I don't want it to conflict with your other classes, period 1, period 4, and so on. But it seems to me that it seems to be okay so far. It doesn't seem like to cause any problem. So I'll leave it as Monday to Thursday. Then Friday will be a helping session. All right. So a helping session, I'm going to tell you on Friday is going to be 10 to 11. So that's how it's going to be. So we're going to keep it at Monday to Thursday, except that Monday will be a different schedule. Monday, I think we'll start at 11:10, 11:15 because of SL Economics. I think she wants to use like from 10 to 11 something, right? So she wants you to be available. So on Mondays, I will move it to 11:10 instead of 10:30. So yes, Madav.
For the helping session, is it still one-on-one or is it?
Yeah,
like
yeah. It'll be one-on-one. So it'll be like the same. Like I'm gonna send an invitation, and if you need help, you just reply, and then I will admit you when it's your turn. All right. So and the other one will have to wait. Yes, Max.
What if we take up a lot of time?
What's that?
What if like we take up a lot of time because we need a lot of help?
Well, we'll see. Okay. We'll take it. Okay. We'll see how it goes. All right. So the helping sessions, like on Friday, I will not go over your Thursday homework. All right. So that will be like for Monday. All right. But I will ask, I will sort of, because that wouldn't be fair because I would have to repeat myself again on Mondays. Right. So, yeah.
Are we allowed to ask anything about the ISU?
No. You should be done with your ISU anyway. All right.
I am done. It's just that I didn't understand 14.6.
What is it?
It's about music theory and open and closed tubes. And
Yeah. Okay. I'll take it up like with the whole class at some point. Okay. So I will see. Like my hope is that we might see each other at least. I don't know. Now you know that you're not coming back on May the 4th, right? So which is a good thing because it's a Star Wars day, right? Anyway, so it's going to be extended for another 2 weeks. And if you ever come back, it's going to be in the middle of May. So my hope is that by mid-May, you may be allowed to come back to school. And then at this point, I will sort of deal with the sound unit. Yes, Catherine.
If we go back to school in May, do we still get to go to Wonderland?
No.
Oh.
You think they're gonna? No, I'm pretty sure they will. They will not allow like big groups like this until I don't know.
Oh.
I'm not privy to their discussion at government, but I would be very surprised if they allow Canada's Wonderland or all those parks to be open until perhaps August, September.
Okay.
Yeah. I'm sorry. No, we won't go. Any other questions? Okay.
Can we go next year? Please.
Okay, like most likely I would have you in like the first semester, right? The fall semester. And well, I don't discount it. Yeah, it could be a possibility. Yes.
Thank you, sir. Let's go.
No, it could, but
Aw.
yeah. I would sort of give you an activity, of course, grade 11 type, because I cannot give you grade 12 because we would not have covered everything, right? Because it closes like at the end of October. So yeah, it could. Yeah, it's a possibility. Yeah, it's a possibility. Yeah, Forrest.
Do you know if we're gonna have physics first or second semester next year?
Like they should always schedule like SL physics fall, because when they schedule it, and they did it once, they schedule grade 12 SL in the spring. It was really hard because I could not sort of cover everything, and it was painful to everyone. The reason why it had been moved to the spring is because math were complaining. Anyway, but I don't think it's gonna occur. So I'm pretty sure like there's very high percentage that grade 12 SL physics will be in the fall. Yes, Leo, you have questions?
Sir,
No?
if we go back to school in May, are we gonna do like all of the?
What's it gonna be like? Well, you're gonna sing "The Lord is risen, Alleluia, Alleluia." That's what you're gonna sing. I'll be able to hear you sing. When we come back, it all depends when. All right. So if we do come back mid-May, so I will sort of go over some question with the sound unit probably, and then give you an evaluation, right? Sound unit. And then I will sort of take up, tying up the loose end for work and energy and power, and probably give you a test. Probably not like super big test. And then by mid-May, if we keep on schedule here, I should almost be able to finish the electricity magnetism unit. So yeah, you might. I'll see if in May I might sort of give you an assignment, right? I may give you like a mini test as well, right? Over the internet online one. We'll see about this. Okay. For now, the important point for me is for you to learn the material so that next year, well, you'll be prepared. You will have seen the material, right? Yes, Eric.
Do you think school will be extended into the summer?
No.
Oh, okay.
Definitely not. No, they will not. They will not do that. Yeah. I don't know what will happen. Like, tell you the truth. Apparently, like the ministry is changing its tunes like from day to day. So I don't know. I even wonder if you're going to get a mark. I don't know if they're for grade 9, 10, 11, not grade 12 though. Grade 12, they have to give a mark, I guess. I'm not so sure for if the grade 9, 10, 11, you're going to get a final mark. You might get like just a fail or pass. I don't know. We'll see. Now, for the record, you all pass, so don't worry. Any other questions? All right. Okay. So I'll stay on here if some people wants. Does anyone wants to take more notes here? No, all good. Okay. So I'll see you tomorrow at 10:30, and so just do like the problems on the website regarding mechanical energy. And use my method here. Okay, so use M. Don't use like use U. Don't use like E. Don't use EG. Use U. Get used to it. All right, and I'll see you tomorrow, guys. So keep yourself healthy and good spirits, and we'll go through this all together. All right.
Bye, sir.
Okay.